When working with polynomial functions, they will always be in this form. This first term is what we call the leading term. And we use it to identify the leading coefficient. The degree of the polynomial is always going to be the highest degree of the exponent in the first term and the term at the end, or the term that does not have a variable assigned to it, is what we refer to as the constant value. The constant value will always be the y-intercept of your polynomial function. And remember, if you are a function, you can only have one y-intercept. We've talked about the various types of functions. Some that we have not discussed and some that we have include the constant function, which is of the form y equals a, where a is some real number. Y equals a, or the constant function, is a horizontal line passing through the point 0a on the y-axis. A linear function is of the form y equals x. It passes through the origin and has a positive slope. A quadratic function, as a parent function, is the graph of a quadratic. It has that indicative U shape to it. A cubic function, y equals x cubed, passes through the origin and has the same behavior as the graph of a linear function, but visually the graph is different. A quartic and a quintic function comes from the highest degree of the leading coefficient, or the leading term. If you notice, as a quadratic function, this has one turning point. It changes direction one time. As a cubic function, this function is going to change direction one time and then two times. And when we say change direction, this graph, if it continued in this manner, would come on down. Or this part of the graph, if it continued in this manner, would go on up. But once it gets here, it changes direction, and then it changes direction to go up. So it has two turning points. A quartic function is going to have three turning points. So to make an exaggerated graph, we're going to start by coming down. We hit a turning point and go up. We hit a turning point and come back down, where we hit a turning point and go back up. Quartic functions are going to have a W kind of shape to them. And quintic functions are of degree 5, and they're going to have 4 turning points. So to exaggerate the shape of our graph, we're going to come up, hit a turning point, down, hit a turning point, up, hit a turning point, and hit one more turning point and go back up. Now, we can generalize the end behavior of different types of polynomial functions based solely on the leading coefficient. We call this the leading coefficient test. If your function is an even degree, so 2, 4, 6, 8, then the ends of your graph will always go in the same direction. If your leading coefficient is positive, then the ends of your graph are going to go up. If the ends of your graph are going down, then that means the leading coefficient is negative. What happens in between will vary. And it doesn't matter what happens in between. What you're concerned with is the end behavior of that graph. If it's an odd degree function, so 3, 5, 7, then the ends of your graph are going to go in opposite directions. If it's a positive leading coefficient and it's even degree, the right-hand side goes up. The same thing is true for an odd degree function. If it's an odd degree function with a positive leading coefficient, the right-hand side will still go up. But since the ends need to go in opposite directions, that means the left-hand side will go down. Again, what happens in between isn't of concern. It's about what do the ends of the graph do. If it's an even degree polynomial with a negative leading coefficient, then the right-hand side goes down. The same is true for odd degree. An odd degree function with a negative leading coefficient, my right-hand side will go down. What that means for an odd degree is that the left-hand side must go up. And again, what happens in between is of little consequence. The number of turning points, as we alluded to in the previous examples, we refer to them as relative extrema. And you can find the maximum number of turning points by subtracting 1 from the highest degree of your function. In addition to the end behavior, we also have zeros or solutions or roots or x-intercepts. Those are all synonymous with each other. A zero to a function is a point where the graph crosses or touches the x-axis. The multiplicity of a zero or a root describes how a zero behaves at that zero, at that point. And we have some overall generalizations to it. If it is an odd multiplicity, then it's either going to cross or sit. If it is an even multiplicity, then it's going to touch or bounce. So if you have a zero that occurs once, so let's say x is equal to 1, and we only have 1 0, then this graph will cross the x-axis at x equals 1. It crosses here. If you have x equals 1, but with a multiplicity of 2, then that means you're going to touch and turn or bounce off of the x-axis at x equals 1. So this graph might look like this. If you have a multiplicity of 3, then you're going to sit on the graph. So at x equals 1, when we say sit, it's an exaggerated cross. So it's going to come up, it's going to sit at x equals 1, and then it's going to cross and keep going. if you have a multiplicity of 4, then you're going to kind of lay on the graph. And this is going to look very exaggerated. But instead of just touching and turning, like you kind of sit or lay at x equals 1 for a little bit. It's going to look wider across this way than it does when the multiplicity is just 2.